So in this next hour, I am going to talk about new quantum security models like that of the pseudorandom functions we talked about in the last hour. So what's the motivation? So I briefly alluded to this when answering one of the questions that came up in the last hour. The fact is we don't really know what quantum attacks on our crypto are going to look like once the adversary gets a quantum computer. And we could imagine that the adversary is somehow able to fool even the classical crypto algorithm into running on a superposition, especially if they get physical access to the object, like it's a smart card implementing a signing algorithm. If our classical crypto is going to be used as part of a higher level quantum protocol, then we'll almost certainly need to consider quantum interaction attacks on it. And then what we'll talk about starting tomorrow is something called the quantum random oracle model, where even if you don't care about these sort of quantum interaction attacks, it turns out that there are some cases where you can't ignore them due to the way we model security. So this is the motivation. So for now, I'm just going to talk really abstractly about why proving security in these quantum superposition attack models can be a challenge. So we have an adversary that, think of the PRF as an example, but we can really think of sort of any setting. They submit a superposition query, and they expect a particular response from the oracle. So they submit a superposition of XY pairs, and they expect to get back X comma YX or O of X, where O is some oracle, say a MAC algorithm or something like that. Now, our goal as we're trying to prove security is to take such an adversary that makes such queries and does something, breaks the crypto system. Our goal is to turn this adversary into an algorithm for a hard problem. So the way we do that is we devise a reduction B that plays the game with whatever supposed hard problem. And B has to somehow present to A a view that A expects. So B has to present to A and query responses that look like we're actually evaluating an oracle on superposition. But this brings up some questions. So, in the case when we're proving security of the PRF, or, more generally, it comes up in many settings. If you're going to do a hybrid argument over the queries that the adversary makes, what does this look like now? So you could interpret a hybrid over queries as sort of a per query security proof, where, the first I queries, you answer one way, whatever the reduction says to do. And then the I+1th query, you answer differently by embedding a challenge from your classical hard problem that you're trying to reduce from. So you might do a per query thing in the quantum setting where, the first query you answer with a value, you just answer the entire superposition with one value V1. The second query you answer with the entire superposition with a value V2, and so forth. And then maybe on the I+1th query, you answer with a value V that was derived from your own challenger. But this presents some problems. So for example, if A actually, maybe they weren't even submitting superposition queries, we don't, they have the ability to, but maybe they're actually submitting classical queries, and they send the same classical query twice. Well, if we're answering the different queries with different values, the adversary would detect that we just changed the oracle that we're trying to implement. Another problem is that actually answering queries answering the entire superposition with a single value actually leads to a rather simple distinguishing attack, even with one query, where the adversary submits a superposition over all X, and they initialize the response registers to just be 0. So in the case where they're given a per query sort of response like this, where all X's are responded to with the same value within a query, what they'll get on the other end of the query is a superposition of all x comma v1. But now v1 is just one fixed value. It's not dependent on x at all. And essentially what you can do is you can throw away v1 without affecting the superposition over x. And you can easily tell that you're in a superposition over x just by doing a Fourier transform or Hadamard operation. On the other hand, if A was actually interacting with the real oracle, what happens is when you respond, you get x comma O of x, where O is whatever oracle is being implemented. And if you think of this O as being a random oracle, let's say, or basically any oracle of interest, these two registers are now entangled. And what happens is if you try to do a quantum Fourier transform or Hadamard on the x's and measure, you will essentially get a random string. So over here, a Fourier transform or Hadamard will give you identically 0. Over here, it'll give you a random string. And you can therefore distinguish the true honest oracle that A expects in the attack from the way that our reduction is responding to the adversary. And if so we could always imagine our adversary doing such a check, and if they ever detect that they're being messed with, if they ever detect that they're not given a true oracle, they could just refuse to cooperate and give up, and therefore we won't be able to actually use A in our proof. So because of this, typical reductions basically commit to an entire function O at the very beginning, an entire classical function O at the beginning, and they use the same function to answer all the queries. Now, this function might not look exactly like the function that A expects. This is where the sort of art of designing these kinds of proofs comes in. But the fact is that the most reductions, until very recently anyway, they just fix one function that defines the oracle's behavior on all inputs and just uses that function through all queries to answer all of the, to answer the entire superposition. This was recently, the term for this reduction was recently coined as a committed programming reduction, and I'll just use this terminology. So a committed programming reduction just means you commit to a function at the very beginning of the security experiment to just use that function to answer all queries. All right, and we will, I think in the very last lecture, we'll talk about non-committing reductions. So this isn't the only way to do things, but it is the most natural based on what we just discussed. Okay, so what we're going to do is we're going to now imagine we're committing to the entire function up front, but this still leaves a problem in the security proof. So I'm going to think of the function now that we're using. So before we had each query, first query is mapped to a value v1, second query is mapped to a value v2. Now I'm going to imagine each input x is mapped to an output value v sub x that we're going to use to answer all queries. But here's the problem. There are exponentially many v sub x's potentially, right? The domain of whatever function the adversary is querying will usually be exponential sized. And so there'll be exponentially many different values vx. The one problem is that if we're going to try to do a hybrid argument over the values that we're using to respond to the queries, well, there's exponentially many such values, meaning we'll get exponentially many hybrids, and we'll end up getting exponential loss in our security reduction, meaning we can't reach a contradiction. There's also just a question of how to simulate efficiently. If v of x is supposed to look like a random function, how do we simulate such a random function efficiently? A random function that we're committing to a function, an entire function at the very beginning of the experiment. We can't, sample the values on the fly. But a true random function, we can't even write it down efficiently because it's an exponentially large object. So there's also a question of how do we simulate this oracle, given that we can't sort of just choose the values as we go on the fly, that we have to commit to the entire function at the beginning. And so we will discuss some techniques for doing both of these today. So let's, our focus is going to be the case of PRFs. we'll see how to resolve the issue for PRFs today, and we'll look at other things next time. So just to recap, the definition of a fully quantum secure PRF is one where we allow the adversary to be a polynomial time quantum attacker, and we also allow the adversary to make quantum queries to an oracle, which is either the PRF for random key K or a uniformly random function R. All right, and here was our construction of a PRF from a PRG that we were trying to prove secure. So as we said before, we can do this hybrid over levels of this tree, where we start with hybrid 0, which is just the honest PRF evaluation, where we answer all queries using the truth table derived from this entire tree. Hybrid 1, we generate the truth table by lopping off the first row of the tree, filling in the second row with random. Hybrid 2, we lop off the next level, fill in the third level with random, and so forth. So as we discussed last time, there's nothing wrong here. This works just fine. Quantum queries, classical queries, quantum computation, classical computation, whatever. It doesn't matter. It's fully black box, nothing interesting going on. So even if we're trying to prove full quantum security, this hybrid makes sense. The issue was the second set of hybrids. So to go forward, what I'm going to do is I'm actually going to change perspective a little, because I think it'll make things a little cleaner. And what I'm actually going to do is I'm going to define a different notion of security for a pseudorandom generator G. So remember, the classical definition of a pseudorandom generator is just this, it's this one-time object where you get either G of a random seed or you get a truly random value, and your goal is to tell the difference. So what I'm going to do is I'm going to give a different definition that's sort of a many-time version, where you get to see many different samples of G. But I'm actually going to not only give you, a polynomial number of samples, I'm going to give you exponentially many samples and allow you to query them on superposition. Obviously, you can't actually learn all exponentially many values if you're a classical algorithm, but I'm going to give you superposition access to these values. So concretely, what this looks like, and here's a typo on my slides, this should be a quantum polynomial time adversary A. So a G is quantum oracle secure if, for all quantum polynomial time A, there exists a negligible epsilon such that, well, what is A doing? A is making quantum queries to either a truly random function or a random function composed with G. So the oracle that A sees is either every value is chosen uniformly at random, or every value is chosen by first choosing a random seed and then applying the pseudorandom generator G. So A is given one of these two oracles, and their goal is to distinguish the two cases. And we say that G is quantum oracle secure if a quantum adversary, even making quantum superposition queries to such an oracle, can't tell the difference. So if we go back to our first step of the classical proof, essentially what the step is doing is turning a PRF adversary A into an adversary for oracle security. And this works classically, quantumly, whatever. And so what we get by running that reduction, the classical first half of the security reduction, is we can convert any quantum PRF adversary A, potentially making quantum queries, into an adversary B for the oracle security of G. So this part is it's just sort of a reconceptualization of the first step of the proof. And the nice thing is that this part is agnostic to the exact query model, because we're really just doing a hybrid over the distributions of oracles, not a hybrid over the queries themselves. So now the next question is, how do we complete the reduction to actually convert an adversary B for Oracle security into an adversary for just the plain PRG notion where you just get a single sample. And in the classical case, it's a very simple hybrid argument. The fact is, so the A is making queries to this Oracle. Every entry on the truth table of the Oracle is just a sample of either PRG or uniformly random. And by being a classical adversary, the adversary can only see a polynomial size set of these values. And then we can hybrid over the Q values the adversary sees. And we can, well, first we can simulate these Q values easily just using Q samples of the PRG or random. So we can simulate efficiently, and then we can hybrid over the Q values to sort of isolate one value that we then use to actually break the underlying PRG. When you move to the quantum setting, however, A makes a superposition query on even if they just make a single query, their superposition query potentially will touch all of these values. And if you think about doing a committed programming type of reduction, if we commit to a function, it looks like we have to, if we want to simulate this perfectly, we either need exponentially many values from the PRG, or we need exponentially many uniform values. And now there's both a question of how to simulate that efficiently, and then also how to do a hybrid that results in a good reduction, because the natural hybrid over all of these values would incur an exponential loss. So our goal going forward is going to be to somehow simulate these query responses of a quantum superposition query using only polynomial number of samples, even though there are exponentially many inputs. And maybe I'll pause here just to see if there are any questions so far. Okay. So our goal is we have some number of samples, and we want to somehow simulate this giant oracle that ostensibly has independent samples in every position. So one extreme is we just use one sample and we plug it into all the entire truth table of this function. Every single input we answer with the same output. But as we discussed before, this is easily distinguishable with a superposition query. Or multiple queries, the other one. So this is no good. The other extreme is where we have an independent sample in each position. But as we just discussed, this incurs an exponential loss if we're trying to do a hybrid over the values. So what we're going to do instead is some sort of middle ground where we have just a few samples, and we place these samples randomly into the various positions. So it's something in between. We're not using the same sample everywhere, but we are using the same sample repeatedly. But we're also not using a different independent sample in each position. And the hope is that by doing something in the middle here, we can both preserve that the number of samples is polynomial, but nonetheless simulate in a way that can't be detected by a quantum attacker. So this leads to this notion that I'll call small range distribution. So the small range distribution is a distribution over functions from some domain represented by this bubble on the left, and some range represented by this bubble on the right. And so the way we're going to sample this distribution is we're first going to start from a polynomial size set of samples, say uniformly random values, or say a polynomial size set of pseudo-random values from our generator. The precise distribution doesn't matter so much. So we're going to start from a polynomial size set of samples. And what we're going to do is we're going to interpret that polynomial size, that small set of samples, as a function from an index space to the range. So if I have R samples, I can view my R samples as a function from a domain of size R, just the numbers 1 to R, into my range, where on input I just look up the ith sample and output it. So that's one component of the small range distribution, is this sort of random function from the small index set R into my range. The other component is going to be a random function from my domain into the index set R of size R. And the overall function is going to be the composition of these two. So to evaluate the function, I first take my random function, I apply it to whatever domain element, I get an index, and then I apply my second function, or I just look up the sample according to that index, and I get my range element. All right, so this is a small range distribution. And now the question becomes, how big of an R do we need to be truly indistinguishable from random? And here's the theorem that that can be proven. We won't prove it completely, but we'll sort of see the ideas, which is that if you have an adversary that makes only Q queries to the small range distribution, to a function sampled from the small range distribution, they cannot, a Q query adversary cannot distinguish it from random, except with advantage or probability Q cubed over R. So Q is the number of queries, R is the size of this this middle index set, and the distinguishing probability is Q cubed over R. Now, this holds regardless of what the output distribution is. Whatever output distribution you have the small range distribution for that output distribution is indistinguishable from the function that just outputs that particular output distribution for every input, and the distinguishing advantage will be Q cubed over R. And it turns out that this theorem is tight. You can adapt the quantum collision finding algorithm to basically search for collisions in these small range distributions, and if you find a collision, that immediately gives you a distinguishing attack. And you can show using quantum collision finding that this bound is actually tight, that there is a distinguishing attack that distinguishes with this advantage. Okay, so now let's think about how big we need to set R in order to maintain indistinguishability. So a natural choice might be to set R to be Q cubed, which means that we get a constant bound on the distinguishing probability. But this might not be good enough, because what might happen is you start from an adversary that distinguishes the probability, epsilon, which is really small. And once you sort of switch to our small range distributions, there's actually, this changes the way the adversary behaves by a constant amount. And it might be larger than epsilon. And so we might not actually be guaranteed to, if we distinguish the original distributions, we might not be guaranteed to distinguish the small range distributions. And if you sort of think about it, any fixed polynomial won't work, because you could always, for any fixed polynomial, the adversary might have a even smaller success probability than Q cubed over that polynomial, and the reduction won't work. On the other hand, you can move to R being something slightly exponential, say, and now you're guaranteed that the distinguishing advantage is negligible, which will allow sort of this part of the proof to go through. But then keep in mind that we ultimately want to do a hybrid over all of the samples that we're using. And here we would have exponentially many samples. So the solution is to not use a fixed polynomial, but to basically use a polynomial that depends exactly on the particulars of the adversary. So what this looks like, so let's imagine actually just stepping through the quantum proof. So we have an adversary that distinguishes a truly random function from a function where each output is independent but sampled according to G. All right, so this is what the first step of the PRF proof gives us. is an adversary that distinguishes these two with probability greater than some non-negligible quantity, epsilon. And now we want to derive an adversary that distinguishes a single sample. So what do we do? So we first imagine on the left, we replace the uniformly random function with the small range distribution, where sort of this output distribution is uniform. By the small range distribution theorem, our attacker can't distinguish these two cases, except with advantage, that should be a q cubed over r. And over here, we get the same thing, except we replace, instead of replacing with a small range distribution with output distribution that's uniformly random, we have the output distribution be pseudo-random. And we get that the adversary can't distinguish these except with probability q cubed over r. Somehow I populated the q squared everywhere, so all these q squared should be q cubed. So we start with an adversary that breaks the oracle security of the PRG with advantage epsilon. And what we get is an adversary B that distinguishes R samples of random from R pseudo-random samples with advantage epsilon minus q cubed over r, some constant times q cubed over r, right? Because that's the only difference now between these two things at the bottom, is we replace the R samples of uniform over here on the left with R samples of pseudo-random on the right. So we easily get a distinguisher that distinguishes both. But we got some error from the fact that we changed to the small range distributions. And now we do a hybrid over these R samples to get an adversary C that distinguishes just one sample, and C's advantage is exactly B's advantage divided by R. So, we get epsilon over R minus q cubed over r squared. And then we can optimize this by setting R to not be a fixed polynomial in Q, but to be Q cubed over epsilon. And again, this 2 should be a 3. And what we get is that the final advantage is actually epsilon squared over Q, again, Q cubed. Right, so by tuning R based not just on the number of queries being made, but also based on the success probability of the adversary, what we get is a final advantage of distinguishing one sample that's epsilon squared over Q cubed. Some interesting things to note here is that this requires knowing the original advantage of the adversary. It's not really a big deal, and we don't really care. And in fact, we can usually fix this by just guessing epsilon to be, 1 over a power of 2. You'll be close enough to the right answer with good probability. The bigger issue with the security proof is this quadratic dependence on epsilon in the final advantage. So what this means is that if the adversary has an original advantage that's something like some pretty small inverse polynomial, the final advantage is going to be much, much smaller due to this quadratic dependence on epsilon. And in terms of practice, if we're actually setting concrete parameters in practice, this is going to mean your need to set the original pseudorandom generator to be even more secure against even smaller advantages in order to maintain security of the final PRF. So let me pause here for any questions. Okay. So I wanted to just, sketch how we might prove the small range distribution theorem. And it's going to include 2 ingredients that will be interesting to note. We won't prove either of these. So the first is this really just a restatement of the polynomial method, which is a known quantum query lower bound technique. And basically what we have is, if we imagine sampling an oracle O from some distribution. So this is a distribution over entire oracles, not just individual outputs. So we sample O from some distribution, and then we have A make queries to this oracle O. Well, then the distribution, or the probability that A outputs 1 actually doesn't depend on the entire distribution, but only depends on the 2 Q-wise marginals. So if I look at just any set of 2Q inputs and ask what's the probability distribution of the corresponding 2Q outputs, the probability that A outputs 1 only depends on these 2 Q-wise marginals. And even better, it is actually a linear combination of these 2 Q-wise marginals. So in the classical setting, this is rather trivial, where actually it's not 2Q, but just Q. It's not hard to show, basically, because a classical adversary only makes Q queries, only gets to see Q input-output pairs of the oracle. You can easily show that the probability of any output is just a linear combination of the Q-wise marginals. When we move to the quantum case, it requires a proof, but you can analyze things and show that actually all you care about is the 2 Q-wise marginals. So we'll just have to take this as fact. We won't prove it. It's more or less just a routine calculation. The other interesting thing that we will use is that for these small range distributions, the K-wise marginals actually are polynomials in 1 over R, where R was the size of this intermediate index set. Right, so we have that the probability that A outputs any value, say 1, is a linear combination of the 2 Q-wise marginals, and then those 2 Q-wise marginals are then themselves polynomials in 1 over R of degree 2Q. And again, we won't prove this. It's somewhat routine. And taken together, since each marginal is a polynomial of degree 2Q, and I'm just taking a linear combination, the probability that A outputs 1 is actually a polynomial in 1 over R of degree 2Q. Okay. So that's maybe something interesting. And now what we're going to do, the way that this theorem works, and the way that the polynomial method more generally works, is you actually throw away a lot of the workings of A and more or less just rely on the fact that A is, the probability distribution of A corresponds to this degree bounded polynomial. We will need to make 2 additional observations. So one is that if I set the index set to be infinity, what I actually get is a truly random function. So if the index set's infinity, what that means is every single input maps to a unique index, at least with probability approaching 1. So every input maps to a unique index and therefore gets an independent sample. So SR infinity is actually a truly random function. So this is important. And then also the other fact that we'll need is just sort of the fact that our algorithm A is an algorithm, meaning its output is a well-defined probability distribution for any integer R. So for any integer R, I consider the small range distribution. I know that my algorithm, it's an algorithm, it has a well-defined output distribution. And that means that this polynomial representing the probability of a particular output has to be between 0 and 1. And so what we're going to do is just relying on these 2 simple things, that our polynomial is degree bounded, and between 0 and 1 for integers R, we're going to bound the difference in probability between P of 1 over R and P of 0. Right? P of 0 corresponds to R being infinity, which is the truly random function. That's what we're comparing our small range distribution against, and our goal is to show that our small range distribution is indistinguishable. So this is all we have to bound now. And remarkably, we can do this. And this might seem quite surprising. So the proof of this is a giant mess. But just to give some intuition why we might believe it, if we think about like a degree 1 polynomial, so we have a degree 1 polynomial, and all we know is that on all these reciprocals of integers, on all the lines that I marked here, this degree 1 polynomial is bounded between 0 and 1. And we're basically asking what's the fastest this polynomial can change. We're asking, for the difference between the value at 0 and the value at some other point 1 over r. So we're sort of interested in the slope of this polynomial constrained between 0 and 1 at these points. And for degree 1, it's pretty obvious what that looks like. For degree 2, you can kind of convince yourself that this is going to be the optimal, to give you the maximum slope. And you can, calculate actually what that slope will be. For degree 3, if you sort of massage things a little, you'll see that the curve looks like this. So see, I'm allowed to actually leave the range between 0 and 1, but I have to make sure I'm between 0 and 1 at a half, and also between 0 and 1 at sort of these points down here. And this will constrain me to sort of look like this. And degree 4 looks like this. And more generally, what we see is that these points, by constraining us to be 0 and 1 at these points, we can't move too fast. We can't sort of have an arbitrarily fast moving polynomial. The higher the degree, the faster we can move, but there's still a constraint. And you can actually, turn this into a theorem that if the degree of your polynomial is less than k, and it's constrained to be between 0 and 1 on all inverses of integers, then you can actually bound the difference as q cubed over r with some constant. I worked out a bound of 27. I don't know what the right constant is supposed to be, but it's asymptotically tight because we know that the quantum attack for collision finding will actually give an algorithm that distinguishes these small range distributions from random with this advantage, meaning we can't possibly improve this. Right. So it's kind of funny, right? If you were to try to prove this theorem this is just a total math statement. There's nothing obviously to do with quantum here. And if you're just given this statement and trying to come up with the answer, you might have no idea what the right answer is supposed to be. But somehow by looking at it through the perspective of quantum algorithms, you can actually, conclude that the right answer is q cubed over r. All right, and so by piecing all these things together, we can prove that the small range distributions are actually indistinguishable from the random distributions and complete the proof. There's one remaining step, which is that the small range distribution actually required random functions, right? This function mapping the inputs to a random index is a random function on an exponentially sized domain, which means just even writing down the random function takes exponential space and exponential time to sort of evaluate. So the question is, how do we simulate these efficiently? But that's actually easy. We can use this theorem based on the polynomial method to conclude that only the two qis marginals matter for any distribution of oracles. And so we can actually simulate a random function by just using a 2qys independent function. And these will look random to any attacker making only q queries. So we start with an attacker. We know it makes q queries. We know its advantage is epsilon. We use that to simulate the small range distribution of the appropriate size r. And to simulate the random function that's a component of the small range distribution, we use a 2qys independent function. And then we sort of go through all the steps of the proof. Okay, so we just covered pseudo-random functions, but really you can imagine superposition attacks against any crypto object out there, pretty much. Secret sharing, encryption, identity-based encryption, authentication, pseudo-random permutations, multi-party computation, etc. And so there's been a lot of literature sort of exploring superposition attacks on various objects like this. We won't, I don't have any time to go into the details, but just know that there is sort of this whole wide world out there, and the techniques are often things like what we talked about, or maybe using more advanced techniques building on these ideas. So let me pause here to see if there are any questions.
There was one quick question. How does, a few slides ago, when you bounded the difference between P of 1 over R and P of 0, does that bound involve the degree of the polynomial, or is the degree just 2q?
Yes, sorry, there was this is a typo. This q should be equal to k here. I switched letters.
Okay.
So certainly the degree matters, and the higher degree lets you get a higher difference here. Okay, so the remainder of this lecture, what I want to talk about is not so much the techniques, but just highlighting even definitional issues. So in the case of pseudorandom functions, it was sort of very natural to ask, what does it mean to have a superposition attack on the pseudorandom function? But when we go to considering other objects, it turns out that even defining what we want to have security under a superposition attack is non-trivial, let alone proving it. And so that's what I wanted to spend the remaining 15 minutes or so talking about. And we'll see how far we get. So let's consider message authentication codes or signatures. The issues are basically the same. So what's the classical security notion? So we have an adversary interacting with a challenger. The challenger chooses a random key k, and then allows the adversary to make signing queries. So the adversary submits a message, gets the evaluation of the message authentication code or signature on that message using the challenger's secret key k. And then the adversary can do it again and again and again on any message they choose. Finally, at the end, they come up with a m star sigma star, so some message and purported signature or tag on that message. And we say the adversary wins if the message was new. So if m star was not one of the queries made before, and also if it passes verification. So if the signature is actually a good signature for the message, right? And we say that the MAC or signature is secure if for any polynomial time adversary, the probability of winning is negligible. Now what happens when we move to quantum security? So if we only care about post-quantum, but want classical signing queries, there's no issues. We're sort of back in the case of the post-quantum PRF. But if we want to allow signing queries, because we're imagining that our signing algorithm is being implemented on a smart card that maybe is being physically accessed by a quantum adversary or something like that, what happens? So certainly the first part of the experiment, there's really no issues yet. We can imagine the adversary making a superposition query. So they come up with a superposition of message comma sigma, and we sign it using the usual quantum oracle notion where we XOR the signature of the message into the response registers. And we can do this as many times as we want. So far there's no issue, right? We just, it's the same thing we did in the PRF case. We just allow quantum queries to the signing algorithm instead of classical. The problem comes at the end. So at the end, the adversary, what do we want the adversary to do? Well, I don't know. Maybe the adversary submits a message signature pair, but maybe the adversary submits a superposition I don't know. Really there isn't a good answer here. It probably depends on exactly how you might imagine the macro signature scheme being used. It's probably reasonable to just assume that the adversary is trying to forge a signature on a classical message. But you could imagine that the adversary actually wants to come up with a superposition of message signature pairs. So I don't know. Maybe we'll just stick with the classical value for the final message. But there's a bigger issue, or more fundamental issue, which is this notion of a message M star being new. So to exclude the trivial attack where the adversary just sends one of the signatures that they got, we require that the M star is different from any of the MIs the adversary queries. But what does this mean now if the adversary is making quantum queries? One issue is that the challenger can't remember what the MIs were that the adversary queried, because the query model doesn't allow the challenger to actually record messages, right? If the adversary were to, if the challenger were to record the message that the adversary queried, you're basically end up violating no cloning if you try to do this, which means that if anything you try to do to record the message will result in the adversary not actually seeing the oracle they expect. So what does it mean that the message M star is new? And to another point to illustrate, I don't think I have, yes, okay, so I do have an example. So what does it mean for the message to be new? So if we consider the following adversary, so the adversary submits a superposition over all messages and maybe initializes the response registers to just be 0. So when the challenger answers this query, the adversary then gets a superposition of messages, comma, signatures on those messages. Now what the adversary does is they measure this incoming superposition, and what they get is a random message together with a valid macro signature on that message. The point, though, is that by measuring this query, the result of the query, what the adversary can output as their forgery looks completely different than the state that they sent to the challenger. The state that they sent to the challenger was this uniform superposition over all messages, and at the end of the day, they just output a single classical message. So by measuring, they certainly changed the state that was signed, right? The state that was signed was a uniform superposition, and they changed it to just a random message. So it's something completely different. And yet, the adversary can always do this, no matter what kind of classical message authentication code we have, the adversary can always do this. There's this notion of a quantum authentication code where the algorithm to authenticate is actually a quantum algorithm. But for the purposes of this lecture, we're concerning ourselves with attacks against classical crypto, and so we don't have the option of running such an algorithm. So there's a serious question here of like, what is the model that we really care about? And to be honest, I don't think that there is yet a satisfactory answer, but I'll give a couple ideas, sort of partial answers. So one is to do this notion of one more security, where you don't explicitly require a new message signature pair, but instead what you say is the adversary gets to see Q message signature pairs through their queries. And what you're going to require of them to do is construct Q+1 message signature pairs. So, basically you're asking them to sign one more thing than they started with. And here there's no issues. We can upgrade this to the quantum setting trivially. We make A makes quantum queries now, but the final query is still classical. And this final win test doesn't have anything to do with the quantum queries other than the number of them. So we can, still test that the MI star are distinct and that they all verify. So one more security sort of trivially upgrades to the quantum setting. And this was the approach Dan Bonnet and I used. But it turns out that this definition isn't satisfactory, because you could imagine a following hypothetical attack where the adversary submits a superposition on messages that all start with 0. And then again in response, a superposition over messages that and signatures where the messages all start with 0. Now, I don't know what the adversary is doing. Maybe they can somehow take this superposition and massage it in a way that they actually get a message that starts with 1 and a MAC or a signature on that message. The point is that because the adversary here is only producing 1 signature, they're not violating one more security. They make 1 query, produce 1 signature. However, this seems wrong, right? This seems wrong that the adversary should see a superposition over messages that start with 0 and produce a superposition where it starts with, or produce a message that starts with 1. In particular, maybe the superposition started with, the preamble for Bob, and then, or from Bob, whichever, and then the adversary is able to massage it to say, for Alice, which would, change the nature of the message. So this seems wrong, and yet it doesn't violate this 1 more security, and so it shows a limitation of the notion. Now there have been more recent definitions which fix this particular problem, but in my own opinion, I don't think that there really is a satisfactory definition yet. Though we've been making progress. So this is sort of, I think, an interesting open question. So let me just talk about some other issues that come up. So in defining security for encryption in the CPA setting, right, so for chosen plaintext attacks, we allow the adversary to make these chosen plaintext queries where they send a message and get an encryption of that message back. And then they make this challenge query where they submit 2 messages and get an encryption of 1 of them, and their goal is to tell which one is the case. Now, when we move to if we want a quantum superposition query, so there's 2 kinds of queries that we, there's the CPA queries and the challenge queries that we can decide to make quantum. If we make the CPA queries quantum, there's really no issue. We can, it's a sensible definition. And in fact, we won't discuss how to prove the security of such a scheme, but you can construct and prove security of encryption schemes satisfying this notion. However, something strange happens when you try to make the challenge query quantum. So if we do the obvious way of turning the challenge query into a quantum query using the usual way that we translate a classical oracle to allow quantum queries, we'd allow the superposition of M0, M1 pairs, and we XOR the challenge ciphertext into the superposition. The problem is that doing so, there's an attack that works no matter what the encryption system does. So what you do is you come up with a uniform superposition of all possible pairs of challenge messages, M0 star and M0 and M1 star, and then you get your you get your challenge response. You get your response to the challenge query where where the challenger XORs the encryptions of MB star, and your goal is to find out which B the challenger used. So the first thing you do is you just measure the ciphertext register to get some C. Then what you do is you perform the quantum Fourier transform or Hadamard on these message registers and measure to get values Z0, Z1. So here's the observation, is that for whatever bit the challenger chose, B, the ciphertext C that you measured actually uniquely determines MB star. Why? Because the encryption is reversible if you have the secret key. So information theoretically, if you have the encryption of MB star, that information theoretically determines what MB star was. And so once we do this measurement before applying the Fourier transforms, MB star actually has collapsed to a classical value. Now what that means is when you apply the Fourier transform to a single classical value, you'll get a uniform superposition up to phase over all possible values, and you'll get something random. On the other hand, M1 minus B, the message that wasn't encrypted, it's not touched. It's not entangled with anything. Nothing happened. It's just it remains a uniform superposition over all messages. And so for the 1 minus B register, when you apply the Fourier transform or Hadamard, you'll actually go back to just a 0 string. So what you get is that the bit B that was being encrypted becomes a random string, and the bit B that wasn't being encrypted becomes all zeros. And this trivial allows you to determine B, thereby breaking security. So the obvious way to quantize the challenge query leads to a trivially unsatisfiable definition. And so the takeaway is that classical encryption schemes are not secure if you encrypt quantum messages. Crucially, if the attacker gets to see the original message registers. This is where the attack came up, because the attacker got to see the message registers that they sent to the challenger, and could then tell whether those messages were in superposition or not. So our solution was just to say, don't allow these quantum challenges. Subsequent work came up with better definitions. We won't talk about them, but they basically came up with a very careful definition to make sure that the quantum challenge query was never returned. And this might sound trivial, but it actually is more subtle than it sounds. And we're basically out of time, so maybe I'll just stop here and say that issues come up also in other settings when you're defining chosen ciphertext attacks, and in other various settings when you're considering quantum superposition queries over classical crypto systems. And so you have to be careful about actually how you model these quantum query attacks. And then once you've modeled them, now you have the question of how to actually go about proving security. And that's what a lot of these works focused on, was both the modeling question and the security proof. So maybe I'll just stop here and take any remaining questions.
Can you just, when you say make sure the quantum challenge query is never returned, can you explain what that means?
Yeah, so it's subtle. So you could imagine, so the normal query model for quantum queries, the response to the query actually includes the original inputs in the response. And this was needed to make the operation unitary. So what you could do as sort of as a first attempt is you could imagine just changing the way you respond to challenge queries so that you don't actually reply with the M0 star, M1 star. Now the challenge query is not answered as a unitary operation, but maybe it doesn't matter. Like, we're just coming up with a security definition. Maybe we don't need to insist that query answers are unitary. This doesn't immediately work though. Or if what you do is you actually have the challenger just, they compute CMB star, but then they keep the M0 star, M1 star for themselves, and reply with just CMB star. This notion is actually mathematically equivalent to just requiring a classical challenge query, because the fact that the challenger kept M0 star, M1 star for themselves and didn't return them is mathematically equivalent to the challenger just measuring the incoming query and making it classical. So if you wanted to come up with an actual a definition that sort of allowed a quantum query, you would need to do something a bit more sophisticated. And you could do things like have the challenger uncompute the MB register, which they can do because they have the decryption key. So from the challenge ciphertext, they can uncompute the MB register and only reply with M0 star, or sorry, M1 minus B and the challenge ciphertext. It turns out in this case, you'll still have an attack. Having sort of either of the message registers is good enough for an attack. So if you want to do something where you don't reply with the challenge registers, but also don't end up being mathematically equivalent to just measuring the challenge registers. You have to be careful. I'm not saying it can't be done, and in fact, that's what this work by Gagliardoni et al. Do. But there's subtleties in making this work that we won't go into. Any other questions? Okay, so let me just skip to the last slide here. So far today, we've mainly focused on these issues that come from actually considering new attack models that might appear when you have quantum superposition attacks. So what we're going to do tomorrow for the security reduction lecture is we're going to look at issues that arise even if you don't change the attack model, but allow a quantum algorithm. So the one example was rewinding, which we sort of mentioned in the previous lecture, and the other example will be this quantum random oracle model, which will be the topic for my last 3 lectures, starting tomorrow and ending on Wednesday. And so with that, I will conclude.